So we shall continue our discussion on classical theory of radiation. So in this video, we'll talk about, as you can see here on the screen, that Stefan-Boltzmann law. Second, we'll talk about the thermodynamic proof of this Stephen's law. And then finally, we'll talk about distribution of energy in black body spectrum. Okay, so our main aim is to discuss these three topics under the unit which we are having discussion for last couple of videos. Okay, so let's begin. So see here, as you can see in the title here, it is shown as Stefan-Boltzmann law. But then first we'll discuss Stephen's law, then we'll come to what is Stefan-Boltzmann law. Okay, it's basically what happened is that energy radiated by a black body, its dependence on the temperature, as we have discussed in the previous two videos. It was first studied by Stephens, and later on Boltzmann continued the study. Okay, so basically first Stephen had studied, and later on Boltzmann had studied this the energy radiation emitted by the black body and its dependence on temperature. So the Stephen's law, it says that rate of emission of radiant energy by unit area of a perfect black body is directly proportional to the fourth power of its absolute temperature. Okay, so when I talk about rate, means it's a, so here since we are talking about rate of emission of radiant energy, so rate means what? It's something per unit time. So the energy radiated by a perfect black body per unit time, then per unit area, okay, because by unit area, okay, is directly proportional to the fourth power of absolute temperature. Okay, so mathematically we can write that this is, so if E represents the energy radiated by the black body per unit time per unit area of the black body, that is directly proportional to the fourth power of the temperature. Okay, so if from here you can see, if the temperature increases, the energy radiant per second per unit area of a black body increases. Okay, which is then, if you put a constant ahead of this temperature term, then which is represented here as sigma, and that is known as Stephen's constant, and value is given by this 5.67 into 10 to the minus 8 watt per meter square per Kelvin to the power 4. Okay, so Kelvin, like, so I say per, so that's why Kelvin to the power minus 4. Okay, so and see here, the main point that you have to note here, this Stephen law talks about the energy radiated by the black body, only that energy which is radiated by the object or the black body alone. Okay, but as you all know, right, this black body has to be in some surroundings, right? So there will be exchange of energy. So it's not talking about that. It's talking about only the energy emitted by the black body. Okay, because see, the idea is what? If you have a black body which is maintained at, let's say, certain temperature, and energy radiated per unit time, that is per second and per unit area, is given by this Stephen's law. But if it is surrounded by, let's say, another black body, or another, meaning the surrounding which is maintained at another temperature, since it is black body, it has capacity to emit as well as to receive radiation. So you can calculate net loss or the heat loss by the black body. So Stephen law is not considered about is not concerned about the net heat loss. It is only concerned about the energy radiated or emitted by the black body alone. Okay, so please keep in mind, and that energy, the radiant energy, we represent by E, and that is equal to fourth power of so that is proportional to fourth power of the temperature, and then we have this constant term, Stephen constant. Okay, E equal to sigma T to the power 4. Okay, so as a note, you keep in mind, this refers to the heat radiation only by the body itself. Okay, not the net heat loss by the body after exchange with the surroundings. Okay, so this is Stephen's law. Okay, so Stephen's law, just to repeat what it says, rate of emission of the radiant energy per unit area by the black body, or in another way to put the things, the energy radiated by a black body per unit time or per second per unit area of the black body is directly proportional to the fourth power of the temperature. Okay, and which is mathematically written in the expression that which we have discussed here. Okay, so then if you now imagine this black body, if you are keeping in a temperature enclosure which is, let's say, maintained at temperature T, and it is surrounded by another black body which I was talking just few seconds back, right? So there is this black body which I am trying to study. It's how its energy is radiated, how the dependence of its energy radiation with respect to temperature. I am trying to study that. So I have a black body then surrounded by another black body, let's say, which is maintained at another temperature. Okay, let's say T naught. So what will happen? So let's say this T is, so the temperature of the first black body which I have considered is greater than the another one. So it will emit radiation. Okay, so the previous theory which we know that. So meaning, if you remember from the earlier videos, like why you feel hot if you stand in front of a fire, and then why you feel cold if you stand in front of a ice block, because there's an exchange of the heat, right, depending upon your temperature difference. So similar thing will happen here, right? So this black body will release the energy or the emission. So then the net loss we can calculate here, right? It's because there are two bodies. So that is given by, so the amount of heat loss per unit area per second, so the rate. Okay, so per second of the first body is given by this, right? So the E, which is the symbol given for amount of heat loss per unit area per second, which will be equal to sigma into T to the power 4, the temperature which is for the first black body, and the T naught is the temperature of the second black body. So basically what is happening, so if let's say I have a temperature enclosure. Let me just show you here. Okay, and I have a black body here, let's say. Okay, so I have a black body here which is maintained at T. I have another black body, let's say T naught. So the energy loss, the total energy loss, or the energy lost per unit area per second by the first black body will be given by this expression. And this is Stefan-Boltzmann law. Okay, so Stefan's law, as you can see, that it talks about the heat radiation or the heat emitted by the black body alone. But here Stefan-Boltzmann law talks about the net loss, net heat loss, or the net energy loss or the heat loss by the black body. Okay, so now we shall see the thermodynamical proof of the Stefan's law. Okay, so now we have to consider a very generalized case here. See, so consider diffuse radiation in an enclosure of uniform cross section. Okay, so we will consider a temperature enclosure, let's say. Okay, so here I have a temperature enclosure whose cross section having perfectly reflecting walls. So these walls of the and temperature enclosure is, assume that all these are perfect reflecting walls, and this temperature enclosure is having energy density U, okay, inside, and then maintained at temperature T, and then let's say volume of this temperature enclosure is V. Okay, so what will happen? So the total energy density within the enclosure we can calculate, right? So because U is the energy density, so the total energy will be energy density multiplied by the total volume. So it will be given by, that will be the internal energy of the system. Okay, so what we will do now, we'll supply some amount of, because we are trying to prove this Stefan's law. Okay, so we'll supply, let's say dq, some small amount of heat from the outside. So what will happen? It will disturb, or it will increase, or it will affect the temperature of this system or the enclosure inside, and also the energy density, right? Because I'm supplying heat from the outside. Okay, so then I have to apply what? First law of thermodynamics, which you all know, right? Okay, so if we apply the, so yes, so it is given here. Suppose dq amount of heat is flows into the enclosure from the outside. What will happen? It will change, or it will affect the temperature as well as the energy density of the temperature enclosure. So now you can apply first law of thermodynamics, which is given by dq, which is amount of heat that is supplied from the outside, and then du then plus pdv, and some amount of work will be done, right, by virtue of expansion of the volume, isn't it? So that is our first law. Okay, so I have to substitute for u, which is the internal energy of the system, the total energy, in terms of volume and energy density. Okay, and this pressure we all know from the previous lecture, where the pressure of a diffuse radiation, because you have considered here a generalized case, which is diffuse radiation, you have radiation from all different directions. So the pressure of the system, or the pressure within the enclosure, will be 1/3 of the meaning the energy density, which we have proved and also studied in the last lecture. So I have substituted this value here, and then later on, see, after this only simple mathematics. Okay, so this will give you the v du, and then there will be two terms using this chain rule, then u dv, and then substitute. So after all, so then this dv dv, if these two terms, if you take common or if you add them up, you will get 4/3 u dv. Okay, so now we can apply second law. Okay, from second law of thermodynamics, you all know that dq is equal to tds, and then this particular expression for entropy, change in entropy, ds equal to dq by t. All right, so dq we have got from this one, right? Okay, so let's substitute this expression for dq in this numerator. Okay, nothing, very simple thing stuff. Okay, v du plus 4/3 u dv divided by t. Okay, then we will again get up this. So from this expression, ds equal to this particular in right hand side expression that you have seen here, one thing we can see that, we can clear from here that the entropy is function of two variables, there is energy density and volume, isn't it? So that's what it is written here. Then since entropy is like a state function, okay, so I can they are meaning exact differential, all these things you know from our basic thermodynamics course. So I can write the total differential for this entropy function, isn't it? So ds equal to, so del s by del u, keeping this v constant, du plus del s by del v, keeping u constant, and dv. Okay, so from this expression now, idea is to what? Okay, so these two expression, if you see the right hand side, so this is ds, this is also ds, these two. So these two expressions are equal, right? So if you compare this, so this v by t, this must be equal to this term, isn't it? Similarly, this particular 4/3 u by t must be equal to this term, isn't it? So I shall write here the same thing. Okay, isn't it? So just I have nothing else. I have just compared both the terms. Okay, whichever is equal, I have just put it here. Okay, so now, as I said, the entropy function, the s is a perfect differential. So this expression holds good. Okay, so this is second order partial derivative, and then this expression, as you know, del by del v, which is then again del s by del u. So del by del u, del s by del v. So this is what. Okay, so now substitute for this del s by del u, because we know from here that this is v by t. Okay, similarly, this expression del s by del v is 4u by 3t. dV by V by T, as you can see after substitution here. Okay, similarly here 4U by 3T, which is we have to differentiate with respect to du. So since temperature T is independent, okay, so the temperature is independent of V, so I can write this like the differentiation of V by T with respect to V will be simply 1 by T, because T is independent of V. However, T is, meaning the temperature is not independent of U, right? Because we know that if you increase the temperature, energy density increases and things like that. Okay, so that's why we have to here again apply chain rule here. Okay, so 4 by 3 is constant, which we take it out. So I have this U by T now, okay, which I have to differentiate with respect to U. So one thing is 1 by T U, because keeping T as a constant. Second term will be what? Second term will be U will be, so U will be constant, then 1 by T square, right? So U will be constant, so it will be, since it is 1 by T, I have to differentiate with respect to U, so it will be 1 by minus actually T square, so that's why, and then I have to write this del T by del U, so that's what has been substituted here. Okay, so I shall write, how should I write? Okay, I should put this one. Okay, so this is mainly because this T, there is a dependence of T, the temperature, with U. Okay, so then after that it is just normal substitution. So I from here to here is what, 4 by 3 I have just inserted it, right? So meaning what will happen after doing this algebra, normal mathematics steps, you will ended up with del U by U for del T by T. Okay, then I will do the integration. Okay, so after integration you will end up see, this is like you have to integrate both sides. Okay, then here you will get, this is ln U, then this is 4 anyway constant ln T, and then I have to put a constant term which is ln A. Okay, so the ln A is a constant which is known as total density radiation constant, right? So I think from here it is easy to understand, right? Like ln U, I can write ln T to the power 4 plus ln A, which is equal to ln A T to the power 4, and then if I compare both this, then I will end up getting this U equal to AT to the power 4. The U is what? This is energy density, which has to be somehow related to, or in fact it is proportional to the energy, the radiant energy or the loss energy, right? So the energy radiated by this black body must be related to this total energy density which is present within the enclosure, isn't it? So that's what, as the radiation loss per second per unit area of the enclosure, there is E, which we have denoted in the first slide of this lecture, in fact the second one. Okay, so there is E, which is proportional to the energy density which is present inside the temperature enclosure that we had taken. So therefore I can write that this E is, so from this expression, energy density is proportional to T to the power 4. That means since energy density is related to the energy loss per unit area per second, so that's why the E also has to be proportional to T to the power 4, and which is, we know that this is Stefan's law, right? So that's how we have proved, I have provided thermodynamical proof for the Stefan's law. Okay, so what does Stefan's law says that energy radiated by a black body per unit time, that is per second per unit area, is directly proportional to the fourth power of the temperature. Okay, so when I write mathematically, then there is a constant term which we represent as sigma, that is Stefan's constant. All right, then now we shall move to talk about distribution of energy in black body spectrum. Okay, this Lermer and Prinshim were the first people who were trying to investigate the the black body spectrum and its dependence on temperatures. Okay, so Stefan had studied how much of energy being radiated, okay, with variable as a temperature, with varying temperature, how much of energy being radiated. Here, what is happening in the spectrum, like how energy is distributed over various wavelength, okay, and how this how this variation in energy distribution is dependent on temperature, right? So that was studied by Lammer and Prinshim in their experiment, and there they had got curves, okay, beautiful curves they have got, which we have know that black body spectrum, okay, nowadays. So here is a plot which shows that, you know, this is this U is the energy density, which is and then in x-axis that you see is lambda in micron, okay. So this plot shows you the variation of energy density with wavelength, and it is represented in micron, and then the different colors shows for indicates different temperatures where the black body is heated to, okay. So, you know, one thing which you have to, like, by looking at this plot, you can see that the distribution of energy is not uniform over all wavelength, okay. There's a certain peak for which for a particular temperature this energy is radiated maximum, the intensity of radiation is maximum for a particular wavelength, okay, for a particular temperature. So that this, let's say for this color, that is where temperature is maintained at 1000 Kelvin or so, so this is a maximum which will represent, let's say, lambda m. This is the peak of this meaning the intensity variation curve. Similarly for this purple color, this is lambda m, okay, which is maintained at 900 Kelvin. Similarly for this green one, which is maintained at 600 Kelvin, this lambda m is here, okay. So first point to be noted that the energy distribution in this black body spectrum is non-uniform over the wavelength. Second thing, initially if you see, for increase in wavelength, the energy density increases initially and it reaches a maximum value, and then again it decreases on further increase in the wavelength, isn't it? Another very important thing, if you can see here, see if I have to mark these peaks of these plots, okay, you will see that as we increase the temperature, the peak intensity has increased, no doubt, which we expect also, right? Because from this Stefan-Boltzmann law, right? So energy radiation, meaning the radiated energy per unit second per unit area is proportional to the power 4, right? So that's why as the temperature increases, energy radiated energy must increase. So the peak of these plots have increased with increase in temperature. That is one thing. Second thing, the maximum of the peaks, or the wavelength, the maximum wavelength for the wavelength for which the energy radiation is maximum, that has shifted towards the lower wavelength side for increasing the temperature, isn't it? So the peaks have moved towards the left side, that means the lower wavelength side, as we increase the temperature, okay. And you will see very interestingly that this lambda m, there is the wavelength for which the energy release is maximum, okay, lambda m, which we represent multiplied by temperature T, is constant. And you will see that this is another law, okay, that we will talk about in the next video. So okay, so I have summarized this the observation of their experiment, Lammer and Prinshim, okay, in a few points. So first point is that for a given temperature, energy is not uniformly distributed in the radiation spectrum, that we have talked about. This is the first thing, as because it's not uniform, you have a certain peak and then come down like that. Then for a given temperature, and intensity of heat radiation increases to a maximum value and then decreases with the increase in, this sort of supplements the first point, okay. Then considering lambda m as a wavelength for which energy emitted is maximum, yes, an increase in the temperature causes a decrease in the lambda m, such that, so this is which I talked about just a few seconds back. So increase in the temperature, decrease in lambda m. So see the lambda m, these dots that you have seen here, they are going to decrease, they're going towards left. So that means the wavelength, that lambda m is decreasing as we are increasing the temperature, okay. That's what it means. as increase in temperature causes an increase in temperature causes increase in energy emission for wall wavelength, which we already meaning we have seen and we have discussed. Okay, another very important point, the area under each curve represents the total energy emitted by the body at a particular temperature for the range of wavelength considered. This area increases with increase in temperature of the body. Okay, so because this is what area under the curve represents what the as it is total energy emitted by the black body, right? Okay, so that also, as you increase the temperature, that will increase, as you will see from the Stephen's law. Okay, so it is found that area is directly proportional to the fourth power of the temperature of the body, which is Stephen's law, as I talked about. Okay, so that this plot in fact verifies experimentally that the Stephen's law, that energy radiated per second per unit area of the black body is indeed proportional to T to the power 4. Okay, so we shall stop here for this video. Then we'll start discussing about another fascinating features of this black body radiation in the next lecture.